Okay, great. Sorry for the delay. Well, I mean, like I said, I really appreciate the chance to talk to you folks. The title of the talk is Exaquest Partner. This is a nonprofit I founded. I'm also the president of it. And if you want a description of what Exaquest is, it's doing long-term biomass storage research as a 501c3 nonprofit. So the talk will hit both of those points. But this is not really meant to be a talk. Like, I really want it to be a discussion. So for me, the slides are just like a prompt for us to chat. And so please interrupt. I did tell John, like, I can't see the chat while I'm sharing full screen. So maybe just jump in with your questions as soon as you have anything that comes to mind. So I've set this up in two halves. The first half will deal with sort of the long-term biomass storage research that Exaquest is doing with the goal of developing negative emissions technology. I'll have like a minute or two just explaining what an NET is if you're not familiar with that. And then we'll discuss Exaquest technology. And then the second half of the talk is meant to talk about why Exaquest became a 501c3 nonprofit instead of the more typical for-profit corporate structure. It's possible we'll kind of get bogged down in the discussion of the technical aspects of Exaquest. So if that happens, I will take the last 15 minutes, 10 minutes, and just make sure I present the 501c3 stuff to you guys, because if some of you are here for that, I want you to get that. And also, if we run out of time, if you feel like you have to drop off the call or whatever, just reach out to me, because it's pretty near and dear to my heart to be able to kind of help people navigate this process. Because it's not as difficult as you might think. Okay, so the first part, and like I said, just whenever you've got questions, things you want to talk about, jump in. A few slides about the background of NETs and how Exaquest is proposing to capture and store carbon. So to set the stage, I'm coming at this with kind of I think about climate change a little differently from some people at this point. And that has kind of motivated why I've gone on to pursue this Exaquest idea. So the way I see it, climate change isn't going away. We really haven't even begun to solve it. Our emission, human emissions, we're at about 40 gigatons of CO2 per year. We're not solving that. We've got 2.5 ppm increase per year in the atmospheric CO2 concentration. You check out the Mauna Loa CO2 graph. So it's bad. It's like so bad that everything we've done in clean tech up to this point is barely making a dent. I take kind of a controversial view of this, that I don't think just cutting CO2 emissions is going to stop, or it's not going to save the world. We're still a world that runs on 8% fossil fuels. We're in the midst of a very slow transition away from that. But, it hasn't happened yet. A lot of things we'd like to electrify, a lot of things, it hasn't happened yet. We'd like the grid to be all renewables, and haven't gotten it yet. I think there are some reasons to be a little wary about the future, about this belief that the transition will just snap into place. I think the three factors for me that really give me pause are, we're still in a world where economic growth is a priority. Not that it shouldn't be, but it is a priority. So that means we're just consuming a lot more every year. That's the goal. We're in a world where the population is still growing. It's not growing exponentially, but it's still growing. So we're at about 7.8 billion right now. We're going to hit 10 billion by 2050. And we're in a world where to feed people and kind of keep the world going, we rely heavily on industrial agriculture. I think some of you here probably are trying to fix that, but we haven't fixed it yet. And maybe there are limitations to what we can do with regenerative agriculture. And then finally, we can't rely on the planet to stop this. So there are drawdown mechanisms for CO2 that nature has. They're just too slow. So we reach the conclusion that we will need to be removing CO2 from the atmosphere with these negative emissions technologies called NETs. So really then the question is, how are you going to do it? I'm not really an expert on the ocean-based approaches. This figure here just sort of provides like a neat little summary of the land-based approaches. Feel free to ask about the ocean-based approaches. I love talking about them. But I guess I'll just pause here for a second. I'm not really intending to explain all of these, but if any of these seem really confusing, feel free to ask. Otherwise, I'm just going to proceed. So you would say, given these land-based negative emissions technologies, how do you tell the difference between them? They all kind of look the same. They all have scientists who support them. All those scientists seem very convinced that their technology is the sort of the silver bullet for climate change. So where do you start in analyzing this? For me, the key thing that I always look at first is the energy cost, right? We'd love to have a magical technology where we capture CO2 with no effort on our part, no energy input, no emissions. We store it again with no cost to us, no energy input, and there are no side effects to that, right? But that technology doesn't exist, and it's never going to exist. There's a cost involved on both the capture and the storage side of things. And obviously, if you're using a lot of energy to capture CO2, a lot of the energy is probably going to involve some CO2 emissions that will reduce your net capture. I think something that people don't think about enough is this distinction between CO2 as a gas versus embodied carbon, CO2 that becomes a solid like biomass or some kind of mineral. Working with gases is tough. And especially for the folks who like direct air capture, there's going to have to be a huge infrastructure around handling pure CO2 gas, compressing it into some kind of liquid form, injecting it underground. So, for those of us who aren't, don't have access to huge resources, solids are much easier to handle. And then permanence is a big one. Some forms of CO2 storage are pretty rock solid permanent. I'd say, calcium carbonate probably is the most permanent form. And then, you start looking at biomass, in the soil or trees, that's a little bit more versatile. And then I'd say there are a bunch of other criteria. And I'm not going to go into detail on these too much because this is where it gets contentious. This is where people really start arguing with a lot of passion about their technologies. So they'll say, well, there are co-benefits of what we're doing. It's going to be profitable. There are no side effects, or there are big side effects. We have a huge potential scale, and we can direct air capture and just suck it out of the air forever. And then finally, they'll say, well, our costs may be high now, but innovation will bring that down in the future. So there's always often there's a push and pull between something being expensive now versus how cheap you think you can make it. So for the technologies that were on the previous slide, I sort of mapped these out on the three main criteria. Something in red is something I consider good, green is good. And I'm not here to promote or dump on any of these negative emissions technologies. The only point I'm really trying to make is that none of them is perfect. All of them have something in red that's not desirable. Exaquest, you would say, oh, but it doesn't have something in red. I would say it eventually does have something in red. Probably in one of these other criteria, like side effects or something. And then the reason why I didn't get into these other criteria so much is if you say take co-benefits as an example, the proponents of any of these technologies will say their technology has co-benefits. So the argument sort of starts to break down. Okay, so that's kind of a little perspective. We can talk about what the Exaquest idea is. And I like to start with the carbon cycle. This is a pretty common figure. In fact, I think this is the Wikipedia figure for the carbon cycle. And the only thing I want you to take away from this is two things. One is that the amount of carbon moving through the carbon cycle every year is enormous. This figure is done in gigatons of carbon. So say photosynthesis is taking 120 gigatons of carbon per year. Bring up my laser pointer here. I'll show that. Okay. So you got 120 gigatons of carbon here per year. You want gigatons of CO2, just multiply that by 3.67, so 450 gigatons of CO2 per year. The other main point to take away is that that's basically balanced by the flux of respiration and then decomposition. So you have plant respiration, microbial respiration, decomposition, and they balance each other out. So you got like 120 going in, 120 going out. And so the result of that is that we tend not to notice the size of these carbon cycle fluxes. They're huge. They dwarf anything that we're doing as humans, but they're kind of in the background. So one is that plants and trees are using photosynthesis to capture CO2. They turn it into biomass, so that's good. Biomass it is stored carbon as long as it doesn't decompose. And so the key of the Exaquest idea is let's minimize decomposition, really target that flux and see if we can do something about it. And then the point I made before about these fluxes being large, this stat we put on our website that biomass decomposition is about 5 times more CO2 every year than our human emissions. So with long-term biomass storage, Exaquest would hope to minimize the decomposition of stored biomass and then minimize any additional CO2 emissions involved in doing that. Okay. If you take this to the gigaton scale, Exaquest is going to impact the carbon cycle. And you wonder, how is it going to do that? So it's a simplified version of the figure you just saw. We're kind of roughly assuming that CO2 uptake and then CO2 emissions are in balance every year. What we're proposing to do is just take, say, 5 gigatons of CO2 equivalent as biomass and move it out of that system and store it somehow, above ground or underwater. You notice we're not proposing storage underground in the sense of like burying it under soil or rocks. I can explain why, but I don't think that's a good idea. Basically, it turns it into a landfill. You know, there are lots of definitions for landfills. Okay, and then to get to the meat of it, it's like, what would this look like as a solution? And I'd say there are 2 pictures you should have in your mind. One would be, clicker will work for me. Okay, a solution we can pursue today. I think we can store dry biomass above ground in some form of container. It's not going to look like any container you thought of before. I'm not going to like make these out of like molded plastic, but some way of containerizing the system so that the whole pile isn't just one big pile. So breaking it up. Here, you know, what I've shown is something that looks like a cone-shaped pile. This is actually a natural phenomenon. Like sand through an hourglass naturally forms a cone-shaped pile, and containers of any kind, if you view them from far enough away, they're small enough, they will also form a cone-shaped pile. Did some calculations on this, happy to go through them if you want, but you could run this on solar power to provide energy to remove water from the system. Say, make it 50 meters tall, with a 200-meter radius here, you're going to have a 31-acre footprint. You could put 2.6 million tons of CO2 equivalent of wood in that kind of a structure that's worth about $50 million, you know, at a pretty pathetic carbon price. Then there's a future solution. I think there's some real limitations on how much you can do on land. So in the future, you'd like to be able to move to the ocean floor. And this is not such a crazy idea because it's the idea driving a lot of the seaweed cultivation as a negative emissions technology. They were proposing to sink the seaweed to the ocean floor. So why not come up with a way to bring wood, other forms of surface biomass, to the ocean floor? And what I've shown here is what that kind of container might look like. And really what's going on here is that you're just trying to create some kind of burial situation within an individual container so that there is essentially sand on top of the biomass you want to bury, and that creates sort of a burial situation. What you're trying to get to is this picture of what, basically where all of the fossil fuels came from. You're talking about plant material that was buried underwater, whether you're talking about coal, natural gas, or oil, that's where it came from. And so research-wise, you just want to know, like, how do you densify the biomass? You'd love the biomass to be denser than water. It's a serious research question. And you'd want to optimize your conditions so that you minimize decomposition, really minimize the production of methane. People often have some questions about Exaquest, just like, so what does this look like? What technology would slow down biomass decomposition? This is sort of the rough picture. Not necessarily all the bells and whistles, but the rough idea is that you could use airflow to remove water from a pile of chips, logs, whatever the biomass is. Ideally, you put them in dry, but let's assume that your system's not perfect and water gets in somehow. This provides a way to remove that water. And then you wonder what the rest of the process looks like. Well, it's really as simple as it gets. You have to collect and transport biomass somehow. That's very tricky. Anybody who works with biochar or biomass-based processes knows the supply chain is very tricky. You would do some grinding because you can't store everything as whole logs. This idea of pressing is interesting because wood itself has a very low nutrient content, but green biomass does not. So green biomass is actually mostly water. Interestingly, the nutrient content of green biomass is mostly water soluble. So it's actually fairly well known in agricultural circles, and you can remove a lot of the protein content of grasses and things like that just by squeezing it. And then you want to sort of optimize some drying technology, hopefully relying on solar energy. And then John Sanchez requested this, so this is my nod to him. He's like, I want to see some calculations of what this looks like at the gigaton scale. So I thought about it. So here are some assumptions here. A dry ton of wood, right, is about 50% carbon. So we're talking about a half ton of carbon in a dry ton of wood. That's equivalent to about 1.8 tons of CO2. If you're storing a mixture of chips and logs, I'm going to assume the density could be about 0.4 tons per meter cubed. That's actually, I think, fairly conservative, but let's just take that as a number. And then suppose you could stack these up in a structure that's 15 stories tall, 15 meters tall. So if you did it, how much space do you need for a gigaton? And the answer is about 10 to 10.7, say 11 square miles, about 7,000 acres. And if you wanted those conical piles I showed before, you kind of roughly double the surface area. You can say that's a lot, 10, 11 square miles. That doesn't sound practical, but, we have a lot of space. California itself is about 164,000 square miles. I'm not suggesting you cover all of California with this, but if you did, you'd store the equivalent of 15 trillion tons of CO2, which is way more than we need to store. Or we probably need to remove like 3 or 4 trillion tons of CO2. And then, think about space that's actually well suited for this type of process, desert space, in just the United States. Here you're looking at a map of the 4 major deserts of the United States, which are kind of conveniently located in California. It's talking about 300,000 square miles just in the U.S. borders. It's 500,000 if you count to Mexico. So there's a fair amount of space available for this. So, I don't know. It seemed like a good time to stop. Hope I didn't go too long. So I'm going to turn off the screen share for a second. And happy to take question.
Yeah, that was great. Thank you, John. Could people unmute and we'll give John a little round of applause first, and then we'll jump into questions.
Hi, Mom.
Oh.
Hi. No one sees you yet.
Oh.
Hi. Hi. I have a question while I'm unmuted. Sure. Would it be possible to put everything in the desert to dry out versus adding energy in the system to dry it out?
Yeah. I mean, that's an interesting question of when you do the drying. Right? Suppose you cut the trees, say in a forest that's relatively close to a desert. You could imagine moving those trees to the desert to dry. That would involve moving some of the water too. So I've always thought maybe you'd want to dry more locally, so you don't have to transport water, which is just a waste of time and energy. But you're right. The desert is a pretty pretty good place to do drying if you wanted to do that.
Mm-hmm. And piggybacking, yeah, sorry.
Thanks. Fascinating idea. I'm wondering if you have looked at the relative locations of forests and places like dry in terms of altitude. Like, are there forests that are high up that you could imagine them rolling stuff downhill or downstream to those locations?
That's a really interesting idea. I think there's something to that in the sense that most of the river systems that I know of in the world they flow out of mountain areas. And those mountainous areas, they're not necessarily the densest forests, but they certainly are forested, a lot of them. That's a really intriguing idea. I've always thought that the transportation issue, the two easiest ways to transport in a low carbon way are probably along waterways, using, say, barges or whatever, or just use railroads. But yeah, not necessarily, I don't know if you want to roll it down the mountain, but you could certainly find where the mountain area drains into and then get it on a boat. That's a really interesting idea.
I guess the caveat might be that those areas are probably already heavily deforested because the access was already so good.
Possibly, yes and no. But interestingly, take California as an example. I don't know how many of you live in California, but we have our huge forest fire problem here in California. Those mountainous areas of California are the hardest areas to remove trees from. There's a big push to kind of thin out the forests and take out these excess trees. That's very, very difficult to do in mountainous areas. It basically hasn't happened. There's not a lot of tree removal going on. So are they the most deforested areas? I would say probably not. I would say the flatter and easier to access the area is probably the most deforested it is. Duncan, did you have a question?
Yeah, thanks, John. That's a fascinating idea. I particularly love the water storage. Reminds me of the whale drop, the dead whale drop, sort of big carbon deposits into the bottom of the ocean. That's my daughter under the table, by the way. That's not. I just wanted to get clear about the process. Is it first dry storage followed by water storage, or is it one or the other?
It's not either or, but they can actually work in parallel. To me, it's very difficult to do research on underwater storage right now, probably because it's illegal. I can't think of a scenario. Maybe if there was a landowner who had some lake or river kind of rights, and they could allow us to try out some experiments, it could work. But we can study above ground storage now pretty easily. Now let's imagine the future where both of these are permitted, which is preferable. I actually kind of lean towards the underwater storage bit. The above ground storage part definitely has ecosystem consequences. You're going to occupy space. It's going to become wood storage space, and it's not going to be what it was before as an ecosystem. With the underwater part, you're going to disrupt an underwater ecosystem too. But what is it? 70% of the Earth's surface is the oceans, and the vast majority of that ocean area is very deep ocean that we don't access very much. So, I guess if you want to combine the two, I've often thought that your above ground storage pile could be like an intermediary. It's like, let's generate like a pile of 5, 6, 10 million tons of wood chips or logs or biomass or whatever. And then periodically we remove what's in the above ground pile, move it to underwater storage. Mm-hmm. So it's a way of generating a supply chain to get to underwater storage. Mm-hmm. Mm-hmm. Yeah, Cassandra?
Yeah. Like building off of Kara's question, what are the elements required for decomposition? Like what are the things that we need to avoid? Like if you drop it in the desert, like does it decompose still, or there's no water so it doesn't? Or
this is, I think I'm going to start adding a slide on this because it's, to me, I guess I've thought about this for a long time. It's not obvious. Okay, so I would say a soil scientist once told me that the 3 keys to decomposition are water, air, and access. So water, because decomposition is a microbial processor, it involves enzymatic processing of the wood. That can't happen without water. Air really promotes decomposition because oxygen really drives the process. So decomposition is much, much faster in the presence of oxygen. It can happen without oxygen. That's anaerobic decomposition, which would be methane. But I guess if you had a choice between the two, you might prefer the very slow anaerobic process. And then the third one is access. So even in the desert, I've actually researched this, there are termites that are like well adapted to desert life. They love eating wood, and they can live in very dry environments. We're talking like drier than any kind of microbe or fungus could tolerate. But with termites, if they can't access the wood, even if a fungus can't access the wood, it's not going to be able to go to work on it. So actually a mechanical barrier can be very effective. So water, air, and access, those are your keys.
Mm-hmm. And any one of those would cause the pile to decompose, or you need all 3?
Well, that's a good question. I think you need 2 of 3. You definitely need access. Whatever wants to decompose it has to be able to access it. And then water or air. One of those 2.
Could you?
I'm sorry.
Sorry, I'm keeping my camera off because of recording. I'm curious if there's any way to combine anaerobic decomposition with like methane-eating bacteria around, or even like in a certain like substrate of a container on the either on the ground or in the water.
Methane? You mean methane-consuming bacteria?
Yeah, eating, it's consuming. Yeah.
Okay, I was just wondering because there are also the bacteria that will generate methane. Okay. Yeah, I would think that would happen sort of naturally, especially in an underwater environment. If you're in an environment where there's a small amount of methane that's being produced, that's a good environment for your methane-consuming bacteria. They'll probably gravitate towards that, enjoy that environment. I see what you mean, though. It would solve the problem of methane emissions getting to the surface. Yeah, you know what's interesting about the underwater part is I don't want to be too blasé about underwater storage, but there are ocean experts who have told me that the different layers of the ocean do not mix particularly well. So once you get below about 1,000 meters in depth, whatever's down there at 1,000 meters, whether it's methane or CO2, takes a very long time to reach the surface and the atmosphere. So there's a lot of opportunities for methane to encounter a methane-consuming bacteria, but they'll definitely want to go where it's being produced.
You might need to go deep enough. You might need to seed the bacteria because they wouldn't be able to penetrate down there because there are striations in the ocean that prevent, especially creatures.
That's a really interesting thought. Yeah, so like in sort of provide like a starter injection of those bacteria in the cube. That could work. Yeah, why not? I think the methane production would happen eventually. So.
Yeah, because I would worry about disrupting other carbon sequestration avenues from the ocean itself, like on a long time scale.
Disrupting how?
Well, just in terms of like changing the sort of natural partitioning of various planktons, or just the sort of horticultural issues like that.
Well, I mean, this is why we're a research nonprofit, because honestly, this is a whiteboard idea at this point.
Yeah.
And I honestly, even if everything were to go right with Exaquest and the policy environment, I don't see this happening for 25 years. I see 25 years worth of legitimate and illegitimate objections to what we'd be doing. There's a lot of inertia to overcome. People, they don't gravitate to the solution we need. But do you see the same issue with the seaweed approach? Because to me, the seaweed people have the same idea, just like dumping it to the bottom.
I don't know a ton about it, but I do know that one of the effects of like ocean warming has been to like repartition a lot of the seaweeds and planktons to less efficient sequesters of carbon and less efficient users of carbon. And so I just, I don't know enough about it. I'm more of an atmosphere person, but like I know a little bit about the ocean. And it just feels like when something's that deep, it's both hard to fix the problem if you screw something up. It's also hard to observe any changes.
Yeah. I honestly, I couldn't even begin to think about it, but I really don't have a clear idea of how you go about conducting an experiment in those conditions. Yeah, but I mean, we're starting to explore the ocean floor. I mean, there's definitely a push for deep sea mining, so people will be down there doing things. It's still a little. I guess my thinking is more on the surface at this point.
Yeah, I think that feels because then at least you can see what's happening, and if there are any consequences, zoom it out.
That's right. Cassandra?
Oh, actually, maybe John's going to say the same thing. I'll let John go for it.
I'm probably not, so you can go first.
Oh,
I got a different direction.
Oh, gotcha. Okay, I was going to say that Veronica Tamsit, who's an oceanographer, was giving an interesting mini lecture on how these experiments happen for dropping stuff to the ocean floor as part of the learning group Ocean channel, if anyone else is interested in that. But one interesting thing we learned from her is that, like, because John, like you said, it's illegal to just dump things into the ocean. So she really advocates for doing modeling first.
Okay.
Yeah, she really advocates for doing modeling first, and she says that, like, so many people want to run these like in vivo studies in the ocean, and it just totally doesn't make sense to her because, like, you should do the simulation modeling, see if it even has the impact that you're hoping for before you even attempt to do like a in vivo experiment. And so I guess that was my question. Like, are you aware of like biomass like simulation experiments, and
Yes.
what's the state on that?
I'll let Elizabeth.
Liz, please. It's preliminary, but there definitely are up and coming. I just finished a program in climate modeling, and there is work in developing like deep sea ocean models to test this stuff at some of the national labs. It's not super fleshed out yet, but that's kind of there definitely are those models that exist.
I guess I would say, I've only mentioned the ocean floor, but actually there are non-ocean floor underwater environments you can consider. Peatlands are kind of an example. Actually, somebody recently sent me Freeman Dyson's original 1979 analysis of how you fix climate change. And one of his solutions was to kind of manufacture artificial peatlands. So find an environment that's kind of like a peat bog, cold, covered by water, and then you get biomass underneath it. Those kinds of conditions could give you the same results in slow decomposition, but without having to go 1,000 meters deep in the ocean. That EM Climate, that's a cool link. I'm going to check that one out. So let's see where. There's another. John, you had a question?
Yeah, I'll make a quick one. I've been thinking about how this compares to something like biochar, where you take the biomass and pyrolyze it, and it's still solid, but like you don't have to worry about like maintaining energetic flow like all the time to keep air out. So yeah. I'm just wondering, like, I don't know the details of the process, I guess, for Exaquest, but like if you have a constant need for energy like year after year to keep this biomass from decomposing, whereas if you had biochar, you just sort of have like this one-time energetic charge, and then it's pyrolyzed and you have a solid that sort of doesn't need to be monitored as much. Like, what's the advantage to not going through the pyrolysis work and maintaining the energy flow like year after year?
Okay, so I'm a lazy guy. Like, to me, Exaquest is all about taking what nature's done the work of capturing carbon. It's made wood. Wood's a reasonably durable material, but it's not perfect. You do have to keep it dry. The Exaquest idea is to do as little as possible, right? Dry it out, create a system that keeps water out. And if you're doing your job well, you don't have to dry continuously, as you suggesting you might have to. But you're right, maybe water gets in, and maybe through our research, we will figure out that this is unavoidable. Now with biochar, you're definitely making a huge investment of energy upfront. Right? Pyrolysis is happening at, I think the lowest it can happen at is like 200 Celsius. But depending on the process, they go higher or lower in temperature. That's a lot of energy. I mean, and a lot of systems will try to use the biomass itself to produce some of the energy, and maybe they'll produce a little bit of surplus. I've made a few attempts to look at papers that produce biochar and see, like, of your ton of biomass that goes in, how many tons of carbon come out in your char. I think it's 1/6. Like, you lose 5/6 of the carbon atoms in the production of the char. Now it may become bio-oil or energy or something else, but the yield of carbon in versus carbon out, I think, is pretty low for biochar. But I'm not here to criticize them, because they do make a product that's pretty resistant to decomposition. I guess one thing that jumped out at me in the recent CDR primer was that the CDR primer was pretty kind of cool on biochar. Like, they did not say that it lasts 1,000 years in the soil. There's actually a fair amount of dispute about how long it does last, because nobody's been able to do the 1,000-year experiment. I don't know that there's a controlled experiment where somebody put biochar in a certain environment in the soil and came back 1,000 years later and said it's all here. So it's good. It certainly decomposes less than your raw biomass, but you're paying a lot to get that up front. And I don't like criticizing technologies, but biochar's been around a while. So Johannes Lehmann was writing his first papers on biochar back in like 2008, 2009, and so they've had a decade of pretty sustained attention to this technology. Actually, I gave a presentation to the California Board of Forestry about a year and a half ago, and a guy from the U.S. Forest Service was there, and he was really down on biochar. He said, we've had years and years of work on pyrolysis, and we've got nothing out of it. Like, it looks good on paper, but it hasn't turned into something that's profitable or practical. So, they should keep trying. Look, there's lots of activity in biochar. There are a lot of startups that are doing it. It just doesn't strike me as something that I'm going to be able to contribute much to. If those people are doing their work, I'm going to do something a little different. If what I'm doing is better, then it'll be good. Cassandra?
Yeah, so many questions. I mean, this is the first time I've heard about, like, the avenue of attack that, like, natural decomposition beats anthropogenic emissions by, it was like 4x or 5x or something like
5x,
that. Yeah, and well, I guess when I heard that, I was wondering, and it sounds kind of terrible, but is there like an additive that you can spray on the biomass to prevent decomposition? Or, like, I know you have a chemical engineering background, and like, what are the thoughts on less natural means of preventing decomposition?
I think that's going to be a fascinating sort of direction of research. So, the wood that you probably encounter in your daily life, I'd say most of it has probably been treated in some way to make it more resistant to decomposition. Anything that's used in construction or furniture has probably been treated with a copper-based chemical that permeates the wood. The copper is lethal to most bacteria and funguses, and so it acts as a pretty good preservative. I guess the reason I've kind of shied away from chemical treatment, at least in my initial thinking, is that if you're going to do something at the gigaton scale, billions of tons, that means your additive has to also happen at that scale. And it might work. Maybe there's a way to create like a gas environment that you store wood in that is extremely hostile to bacteria and funguses. But I'm not going to count on that immediately. I guess, to me, that's kind of like a second order question. If you can store it dry, you're already solving, to me, 99% of the problem. Maybe the additive allows you to, maybe it would allow you to store wood in Brazil, a place that's extremely humid.
Yeah, so I guess my thinking is like having, I'm new to this space too, but I guess I'm realizing that like, I think we have to harness existing industries, and we have to give someone a way of making some sort of money, or else it's not going to happen. So I'm just like looking at all those big chemical companies, and I think they would want to get in on like making some sort of like treatment chemical to prevent decomposition. And like, I think that's the only way we're going to reach scale, if we like let existing industries get like a piece of the pie.
So I think interestingly, we're kind of segueing a little bit to the nonprofit topic here. One, Exaquest is first of all, it's not a business. I'm not hoping to get rich off of this. I would say my biggest dream for the idea would be that I do it. We make some attempt to do this, and it causes an uproar, just like massive scientific criticism of people saying that's horrible. You're doing it all wrong. You should do it this way. Because that's really what I want to achieve. When we get in people's heads, especially the heads of the smartest people in the world, and get them, if I'm not doing it right, tell me how to do it. Like, because I think it's definitely a new approach. It's not being considered in things like the CDR primer. But it's also not getting a lot of research attention. I would love to get into their heads and make them want to make this better. If they start putting time and effort into making this approach better, I would be very happy.
Mm-hmm.
But you're right. If it's going to be profitable, sure, yeah. I think some kind of angle that appeals more to an existing industry. Yeah, I can see that being important.
Mm-hmm.
I did make my promise about the nonprofit angle, but Archie, you have a question?
Yeah, sorry, another one. Really quickly, I just wondered if you could talk about additionality here. So, if I've understood correctly, really you need to be growing these trees before you put them in your bunkers. Is that right?
That's right. Okay, so I've stayed away from this jargon, but like, could you tell me what you mean by additionality, and I'll address it.
Yeah, so I guess one worry would be you have all these trees and they weren't going to decompose in the next 15 years anyway, and then you cut them down and you put them in a bunker, and actually all you've done is remove the sink of carbon they were constituting once they were alive without actually preventing the decomposition.
This is a very good point. No living forest should be cut down. If the forest is growing and healthy, to me, Exaquest is a complement to reforestation. We should reforest the planet, and then instead of giving up on the trees that die naturally, we find a way to extend their sort of shelf life, the shelf life of their carbon. Okay, to me, this seems like an easy thing in California because there's a natural drive to want to remove trees from forests in California. So there's lots of tree thinning going on. In other places where forest fires are less of a problem, I think if you talk to any kind of tree expert, they will tell you that pests and diseases are a massive problem in forests right now because of climate change. Climate change is changing the environmental conditions for trees bringing in new pests, new diseases, which are killing tons of trees, and it'll take time for forests to adapt to that. So focus on the dead trees because they're the ones that are going to rot. So yes, very good point. It's don't cut down a perfectly healthy tree.
Can I ask? So what happens if you take all the dead trees out? I mean, those were food for something. I'm assuming. So what happens then?
It's a good point, but you could have a little bit of an argument about this. I don't think you need all of the dead trees to stick around, right? So you don't want to. It's a lot of effort to go into an ecosystem and just go hunting, relentlessly for every dead tree that could be stored, and to then store it. I think inevitably, you're probably, if you were lucky, you get half of them, 50%. So even with your best efforts to find trees that can be stored later, there's still plenty of habitat and ecosystem for things that want to decompose. I do kind of take issue with this idea that say a tree trunk that falls in the forest, the decomposition that happens to that tree trunk is, in my mind, not particularly relevant to the soil. So by all means, don't take out the roots. Leave the roots in place, let the roots decompose. But the trunk itself was going to decompose on the surface. It was going to be a nice habitat for funguses, some mushrooms grow, but taking that away to me is not, it's not like lethal to the ecosystem. And like I said, even if you tried as hard as you could, I don't think you're going to get all of them, like not even close. EM, did you have a question?
Yes. Yeah. Lovely presentation. I'm sorry, I'm just getting another meeting ran over. The one question I did have, maybe you already answered this, but similar to one of the last questions, have you considered what material you would use for such a structure? It sounds like that actually might be like a key part of what is planned, and also might be a challenge in terms of like embodied carbon. And a little bit of an add-on too, like you just briefly touched on like transportation logistics, and that also sounds like it could be a big challenge in carbon emissions.
Just a quick point on the transportation logistics. You're absolutely right about that. I view Exaquest as primarily a local solution. So the idea that you're going to transport biomass hundreds of miles, unless you're going to the Mojave Desert, is probably not worth it. The container issue. There is a material we have in the world that's impermeable to water and gases that we're drowning in. It's plastic. There's so much waste plastic in the world. It is astounding. And most of it can't be recycled because if you want the properties of plastic to remain constant after you melt it down or recast it, it doesn't really work very well. But if all you want is a barrier, like just a plank or a wall or something that gives your container shape, I mean, I can't think of a better use for waste plastic. I mean, it seems to me like the perfect material for that. That's a long way down the road. In 10 years from now, we'll have the pilot plant, the pilot project where we're, recasting plastic on site, and we're really going to a big scale. But
there are microbes that do eat plastic. So then what?
Well, that's true, but those microbes, to my mind, they're not very abundant. But even if they were abundant, it's the same issue that you have with all decomposition. It doesn't happen just magically. It's a biological process. It involves water, mostly. So deprive the system of water, and you will do quite well. Should I know some of you almost certainly came to hear about the nonprofit bit, so can I take a few minutes on that? Okay. So I'm going to reshare my screen. Hopefully here with the light. Okay, is that full screen for you guys? Yes. Okay, great. Okay, so why we chose to be a 501c3 nonprofit. Okay, and the number is 501c3. That refers to a section of the Internal Revenue Code that describes a kind of nonprofit organization. It's the most common kind. It's almost certainly the kind that you want. Okay. Well, as I get into this, I think I need to start by just saying why we chose not to go the for-profit way. And that involves a little bit of discussion about for-profits versus nonprofits. So This will seem pretty obvious to most of you, I think. There are some real advantages to being for-profit. You have the profit motive. You know if you're doing well, you're making money. Investors, they follow a playbook. There are rules for how they get involved in your company. They have confidence and trust. There's the free market. You're picking winners based on who's profitable or not. And then you get this private ownership of intellectual property, which incentivizes innovation. I've heard people say that they think there's not a lot of innovation in the nonprofit world. And I guess if you take this seriously, then I could see why you believe that. But when it comes to the clean energy CO2 removal space, I think there are some real limitations. So let's take those four issues again. So you got the profit motive, which is fine. Profits are good, but you're now competing with companies. You're a company that's trying to minimize CO2 emissions, remove CO2, but you're competing against companies that don't care about that, and they're not penalized for it. So you're already at a disadvantage. Your investor playbook gets a little messed up because investors are confused. They're being told that they should invest in these companies for some altruistic motive of saving the world, but the economy is not set up for that yet. And so I think what you see now is a lot of uncertainty among the investors. They're getting into this, but they're kind of like putting their toes in, and that's about it. Not really jumping in because they don't see the profits yet. Your free market invisible hand still works, but it's not particularly picking the clean energy companies or the CO2 removal companies. And as a result, you have these companies needing to rely on subsidies, or they're waiting for a carbon price. They need a little bit of support or patient investment. But that's not that's not going to be the thing that drives massive investment. And innovation, tackling this problem of innovation, because you're operating in a low profit field, investors are scared, basically. That's the main reaction I've gotten when I talk to investors. And if you tell them that your technology is not ready to go right now, they're really scared. Some of you are too young for last 2 6 today. There was $25 billion invested around 2008. The return on investment was very poor. It was they call it clean 1.0. So Exaquest used to be nonprofit. Well, we got stuck on this innovation hook. So, let me add the point that because investors are scared away from R&D, they now rely on the universities and the academic world to do the R&D for them. And I've just come out of Stanford, where I was doing PhD research until I decided I didn't want to do it anymore. I saw it happening in my own lab. Total, the French oil company, showed up, talking to my research advisor, saying, "We like what you're doing. You're doing some really cool CO2 conversion research. We want to provide an investment for you to do kind of research that leads to commercializable technologies." So we were literally getting money from Total to basically be their R&D team. And they were going to get a pretty good slice of the intellectual property, but they don't want to do this themselves. They probably just saw grad students as cheaper than people that had to pay on their own. Anyway, so with long-term biomass storage technology, the investors looked at it and they said, well, why don't you get some scientists at the university to figure this out first? And honestly, I couldn't blame them. I view that as just logical risk aversion. If I were an investor, I wouldn't want to spend money on it either. Now, the really interesting question is, why aren't academic scientists interested in this? And I think I have a few ideas at this point. First of all, I think the time horizon of the research takes too long. And at least from the kind of research background that I was in, where you're looking in labs, the idea of moving out into a field environment is pretty intimidating. So take those two together, intimidating environment, long projects, and it doesn't work. These people are in the public or perish world. Biomass storage is also, I think, generally viewed as an engineering challenge. We've been talking about things like logistics and transportation and drying, and these are things that engineers deal with. Scientists hate engineering. They think it's boring. They didn't want to become engineers. So it's not sexy to them. And I would say the nail in the coffin is that there is no famous person out there who is banging the drum for long-term biomass storage. It's really interesting how just one person can have a huge impact on the field. In biochar, I think of Johannes Lehmann at Cornell. For something crazy like solar radiation management, David Keith at Harvard has been amazing. Like, without David Keith at Harvard, I don't think solar radiation management research is happening today. But one guy who really believes in the idea can push something really far, and we don't have that. Right? Exaquest doesn't have that. But that doesn't mean we can't create it. And so there's a gap. There's a gap where academic scientists are not working, perfect opportunity for a nonprofit. Now, advantages. There are definitely some advantages of being a nonprofit. To me, the biggest one is fundraising flexibility. So, especially when it comes to research funding, you're basically dealing with the government most of the time if you're a university professor. Occasionally, you may get some input of money from the business world, some kind of interest, in something. You never raise money from the general public. Nonprofit, you know. It's a huge untapped source, especially for an issue that research freedom. I think how many of you are from the academic university research world, that it can actually be kind of shocking sometimes how much the realm of encouraged research is circumscribed by the funding agencies or the program agencies. In the nonprofit world, no one cares what kind of research you're doing. The IRS is completely agnostic about the topics of research. You're really only answering to your donors. If they don't like your research, they just won't contribute. You get favorable tax rules. So Exaquest is tax exempt. We don't pay income tax or sales tax. We don't sell anything, but no taxes. The donations that do come in, the donors get to take a tax deduction on those contributions. And then I think this is a big one, board independence. So I don't have personal experience from being inside a startup, but it appears to me that at some point your founders start to lose control of the company. And they have to do it in return for money. Investors need for no equity. So eventually, people want to make a business go. And then with a nonprofit, it's not profit. But if you don't have members who elect the directors, the board doesn't answer any. There's obviously rules that they're allowed to operate, but beyond that, they're pretty much independent. And so Exaquest's board of directors can perpetuate itself indefinitely if we want it that way. Some real disadvantages. I'm going to put right up front paperwork. Paperwork can be done. Bureaucracy can be dealt with, but it's a little scary. And I have a background as a corporate attorney, so I can deal with this. It's very annoying for me, but huge barrier to entry. You also have the needing to fundraise continuously. Donations need to be raised every year. It's not like a business in the sense that business can go on autopilot at a certain point, make its own money. But then fundraising, the opportunity to get new donors can also be an opportunity. You bring in somebody with a huge pile of money to support things. Here's a big one for if you're doing research. My view of how research nonprofits work is that I think they basically have to be open source. This idea that you would do research as a nonprofit, patent something, or take your results and sell them, or make money from patent licensing, I don't think the IRS is going to permit that. So I think we chose our open source research model just to avoid any questions. And then for most nonprofits, especially for us, your activities that are not related to your mission are pretty restricted. There are ways for nonprofits to make money. So a museum can sell tickets, the orchestra can sell tickets, the school can charge tuition. But the reason they can do that is because what the revenue that they're receiving is in return for executing on their mission. So it has to be rare. But it's to me that I do that. And I make time available for people who stuck around for this part. I'd love to mentor anybody who's trying to get into starting a nonprofit because it can almost look impossible at the beginning, especially if you don't have the resources. And I guess I can tell you that I did this basically on my own. Exaquest has no employees. We have our board of directors, myself as president, and then the same person can't be all the officers, so I brought in my father to serve as secretary and treasurer. Small operation, but I've been able to do this myself. And I'd like to help you do it too. So how do you do this? Well, the first thing is you have to choose your purpose. So you have to fit within one of the categories that are allowed to become a 501c3. And I highlighted charitable and green here because to me that's the biggest catch-all category. There are many organizations out there that have a climate-related mission, and it's not, you'd say, I don't see climate on this list, but I believe that climate fits into the charitable category. Obviously, Exaquest has a scientific mission, so we kind of fit into one of the well-established categories already. Then obviously incorporate, and then your most important decision is picking your board of directors. Because the board of directors is going to run the nonprofit. The board of directors will hire the officers, fire the officers, the president, secretary, treasurer, etc. You do want your directors to bring some kind of competence to the organization, some kind of skill, but it's really, really important to trust them and to have a set of shared values. You kind of have to agree on the game plan going forward before you bring them on board. Then you apply to the IRS. There's literally a form. It's called Form 1023 that you're going to file with the IRS to become a 501c3 organization. And the big determination the IRS makes is whether to label you a public charity or a private foundation. You want to be a public charity. Public charity is the kind of organ that raises money from the public. Dollars into some kind of organization that then spends it. Even if you think you don't need that much money, the paperwork of being a private foundation is like scary, even for me. And then, obviously there are many, many steps I'm not listing here. Those are really just like box ticking things. The key to getting through all those additional steps is just be patient and diligent. A nonprofit is different from a for-profit in the sense that if you walk away from it for a few months and just, life happens, you can't work on it, nothing really changes. I mean, over a period of years, if you ignore your nonprofit, the IRS will take your tax-exempt status away. But it's not like a for-profit in the sense that it must happen now. Like, you must hit these series of metrics right now. And I see that, I feel bad for these guys trying to commercialize technologies. And it may work, and they get rich, but they're under tremendous pressure. Get your Series A for $50 million. Those investors expect results. They want to see revenues. They want progress. Sometimes science that way. It doesn't take a review of research. If it works and if Exaquest sort of catches on as a thing for the rest of my life, somebody but I have no trouble pursuing this the rest of my life. And so really it's all about your commitment to the organization. If you're willing to stick with it, then the nonprofit can persist, even with very little in donations. There's no rule that says a nonprofit needs to have X dollars in donations to survive. You just need to be able to pay your bills. And that's it. I put my email address here. I will stick around for anything you guys want to talk about. I'm going to stop the screen sharing. Did I stop it?
Yes, it stopped. And thank you so much, John. And yeah, super interesting. Ooh. I will also pause the recording, if that's okay. So I do have to drop off as well.
Richard, you